Welcome to our backyard. This is the Backyard Philosophy Podcast. We are two friends having a discussion after everyone else has passed out or gone to bed. Grab a drink and listen as we discuss everything from automation, space exploration, and why the meaning of life is 42.
In school, we were all taught that there are four states of matter: gas, liquid, solid, and plasma. But what if I were to tell you that you were lied to, that the education system failed you once again? And there's not just four states of matter, but in fact 30. And we're discovering more and more every day. States of matter that can bring science fiction and the impossible to life. But before I tell you the basics of the weird, strange, and out-of-this-world states of matter, Nick, how are you doing? What are you drinking?
I'm doing good. I'm not that surprised about the education system once again, and I'm drinking some coffee and Jim Beam.
I am joining you with the exact same thing, coffee and some Jim Beam. Great minds think alike, I guess. Ugh. But before I begin, I want to set the stage. Many of these states of matter are only possible in laboratory conditions or extreme events, or even just theoretical. But the math pans out, so theoretical is probably right. And I won't be going into how to make these odd states of matter or how they might be used in the world. This is kind of more of a quick synopsis of what the hell are these things, so to speak. And if people like it, I'll go more in depth about the states of matter and what it could mean to the future, but let's just get everyone on the same page. First, let's talk about liquid, gas, and solid matter for a second. Solid matter is molecules or elements arranged tightly, but they're still vibrating, they're bonded together, so they're moving technically, but still constricted. Then we have liquid, which is the same molecule or atom, but they're not all connected, they're more loosey-goosey and free. Then we have gas, which I would say are more independent atoms and molecules, just kind of doing their own thing. Good. Now with that out of the way, let's start getting weird. Let's start a simple amorphous solid. Now, you may not have heard this term before, but you definitely interact with this state of matter nearly daily. Amorphous solid is similar to a normal solid, molecules packed together, not really moving around or loose. But an amorphous solid, unlike a traditional solid, is organized in a lattice pattern on a molecular scale that is nanocrystalline solid. So that's just a bunch of fancy words for saying the atoms are not connected in a basic structure that is organized. And to help simplify this, I want you to imagine two pieces of paper. On one piece of paper, someone has drawn a bunch of hexagons, all the same size, all the same lengths, all connecting, all very neat and tidy. That is your traditional solid. Now on the other piece of paper, I want you to imagine a bunch of hexagons, all connecting, just like the first one, but all the sides of the hexagons, they're all different lengths, different angles, some are squished, some are elongated. That's the difference of the structure between a solid and an amorphous solid. Now I mentioned that you interact with them, the amorphous solids, nearly daily, which is more than likely true. Amorphous solids are materials like plastic, glass, and gels. So we've all heard before that glass is more of a liquid than a solid. That's not really true. It's more of a solid than a liquid, but how the particles are arranged are non-traditional to what we would classify in science as a solid. Which kind of leads us to crystalline solids, a brother, so to speak, of amorphous solids. When you hear crystalline solid, you might think, crystalline, crystals. You might think of crystals. And you, ladies and gentlemen, would be correct. Crystalline solids are things like diamonds, salt, quartz. They're solids, but how their molecular structure is arranged makes it a crystalline solid. So they're a solid with rules, so to speak. They are rules like atoms and ions have to be arranged in a definite and repeating three-dimensional pattern. So imagine the hexagons on the piece of paper like we did with amorphous solids, but the tidy hexagons, the one that are all same length, same size, but now 3D. They're all uniform. They're all going up. They're going from a 2D organized hexagonal structure to a 3D hexagonal structure. So instead of the bonds being connected on a single plane, they're connected on multiple planes. That is a crystalline solid. There are other similar structures in states of matter to amorphous and crystalline solids, which I'm kind of going to skip over because states of matter like plastic crystal and quasi-crystal are more or less the same as crystalline solids and amorphous solids, but it just breaks down to their molecular structure and bonds rather than what we would classically think of states of matter, like completely different 180. So I'd like to jump into things like non-Newtonian fluid. Non-Newtonian fluid, you might be familiar with it. If you're like me and you grew up watching Mythbusters, you definitely have heard of non-Newtonian fluids, and you've probably interacted once or twice with non-Newtonian fluids. Non-Newtonian fluids come in different shapes and sizes, but the most common ones that you might find in your kitchen are cornstarch and custard powder. Non-Newtonian fluid is a fluid sometimes. It really comes down to pressure and temperature. Non-Newtonian fluid is a fluid sometimes, but when things are warm, relaxed, it becomes that liquid. When it's cold or it gets hit, it acts more like a solid. I guess the best way to explain it, now this is just an example, so it's not exactly like this, but I think this explains non-Newtonian fluid pretty well. Think of the muscles in your body. When you're laying in the sun, not moving, no stress, maybe a pina colada in your hand, or some Jim Beam and coffee like me and Nick, you're relaxed, you're loose. You melt into your chair, into the sand. Your muscles are at ease. But when it's cold outside and you're all scrunched up trying to get warm, you're all stiff and solid. Or when someone's going to punch you in the arm, you flex up and tense. That's just like non-Newtonian fluid. When things are warm and peaceful, it flows like a liquid, nice and chill. But when you hit it hard, it flexes and stiffens into a solid. So with non-Newtonian fluid, if you run hard enough, like your feet into it, you can actually run across this fluid. But if you're relaxed enough, you'll sink, almost like quicksand, so to speak. Does that make sense to you, Nick?
Yeah, that makes a lot of sense. I can picture what you're talking about. Kind of went away there when you're talking about sitting on the beach and started thinking about other things, but we're back now.
It's a cold season for both of us, so I guess we're both missing summer.
And also, I only encountered quicksand one time in my life, and I'm kind of pissed I haven't encountered it more. Indiana Jones made it seem like it was going to be a lot more prevalent in my life than it really is.
Now, we just went from solid and liquid with non-Newtonian fluid. How about we go to liquid and gas with supercritical fluids? Supercritical fluids, again, this is a simplified explanation, are when liquids or gases like acetone or carbon dioxide are subjugated to high temperature and high pressure above their critical points. And when supercritical fluids are near gas, they simply act more like a gas, and vice versa. When supercritical fluids are near liquids, they act more like liquids. So fun fact, supercritical fluids apparently are really, really great at dissolving and mixing stuff. I have no idea why. Trying to understand all this physics, it's a little bit difficult. But supercritical fluids, it's a product of its environment pretty much. Depending on the situation and where it is and what other things are around it, that's more it becomes. It becomes more of a gas or more of a liquid. And I think this is a good precedent just to say, in engineering and science terms, when someone says a fluid, that doesn't mean a liquid. Fluid can be gas or liquid. Fluid, when you're thinking like drag in the air from an airplane, is a fluid because the air is acting on that airplane. Is the same as water on a boat. They're both considered fluids, but there might be different states of matter like liquid and gas. So fluid in the science and engineering world is kind of a little bit broader category. So keep that in mind as we press forward. So sticking with super, we went from supercritical fluids. Now let's go to superfluids.
These are fluids that are less judgy.
No, they're molecules wearing a Superman cape. Come on. But superfluid is when certain elements are brought to a specific state, usually just above freezing or close as we can to freezing. And by freezing, I mean absolute freezing, near 0 degree Kelvin. Now, that is cold. Like 0 degrees Celsius is 293 degrees Kelvin. So I just want you to imagine how cold absolute zero is for Kelvin. But when isotopes of, say, for example, helium or other elements, but when those isotopes of helium are cooled, that gas turns into a liquid, sort of. That liquid is kind of transformed into a fluid state, so still kind of acting like a gas and a liquid. But the most important thing, I think, about these superfluids is they have zero viscosity and therefore have no loss of kinetic energy. Once again, that's just a bunch of fancy science words for saying it's kind of frictionless. So imagine a glass of coffee and you put some Jim Beam in it. You put your spoon in it, you stir it around. Eventually, you put it on your desk, the coffee, the Jim Beam will come to a standstill. With superfluids, if you stir that in a glass, like a cocktail, just like coffee and Jim Beam, that zero viscosity fluid, that superfluid, would continue to spin in a vortex forever. Or at least until it warms up or something came along and changed the state of matter. But it'll keep spinning forever, which is crazy to think about. And this is a little bit sidebar, but when you supercool helium, I really like weird scientific experiments, but when you supercool helium, it has a tendency to fall through solid objects. And what that means is if I put supercooled helium in a test tube, it would kind of fall through the test tube. Weird, Nick, right?
That's awesome.
Yeah.
That's hilarious.
So I can imagine studying it as a researcher is got to be annoying. Like, God damn it, how many... I keep pouring this in and it keeps going out. It's like a magic trick. But alongside with superfluid is another form of matter called the Bose-Einstein condensates, or simply known as the BEC, are kind of considered a superfluid. So I'm not quite sure how they classified it into different states of matter, but they are considered a different state of matter. Bose-Einstein condensates, this kind of weird state of matter, is, well, let me give you an image, and maybe this will explain how it interacts with the world. So imagine a room with a bunch of atoms. They're all kind of doing their own thing, you know, like a party. Some people are sitting on the couch. Some people are chugging out of the keg. Some people are just talking in the kitchen. You know, everyone's kind of doing their own thing. They're all in the same area. They're all human beings, so they're all similar, but yet they're still doing their own thing. Now with atoms, it's the same thing, but they're bouncing off the wall. They're standstill. They're gas. They're particles in a container, just like humans at a party. But once again, when these atoms or people are brought to close to absolute zero, again, Kelvin, it makes the atoms get in order, so to speak. So rather than everyone doing their own thing at the party, or all the atoms doing their own thing, acting independently, they unify. They kind of act like one big atom, one big organized group. So this house party you're at with all your friends and family, just everyone independent thing, all of a sudden turns into one entity, one drill instructor, so to speak. So if you move one, all the rest go with it. It's like if you have a bunch of images on a PowerPoint and you select all and you create a picture so they're all just one independent image and you move that around, they all move around with it. It's one entity. That's what happens with Bose-Einstein condensates when you bring it to the atoms to close again, once again, to 0 degrees Kelvin. But that was so weird to me that when you freeze these atoms on a quantum level, they are all unified. They all become together. They're not independent entities anymore. They're one entity.
It's the atomic equivalent of trying to format a Word document.
Yes. That's a great example. But speaking of the quantum level, we should talk about the quantum spin Hall state, which I'll be very honest with you, Nick, and all you listening. I don't get it.
It sounds more like a nightclub than a state of matter, if we're being honest.
Well, I understand the words, but I'm not comprehending the concept. So, all right, so quantum spin Hall state. All right, Hall. I know Hall has to do with magnetism. the Hall effect, et cetera, et cetera. State, okay, it's a state of matter. Quantum, so it's at the quantum level, so it's dealing with small particles, quantum particles. And spin, which way the particles are spinning, are they spinning up, down, or strange? So I understand that it's something to do with magnetism affecting the quantum state particles and their orientation of spin. I think it's, yeah, I believe it's up, down, and strange are the three spin cycles for quantum particles. But I don't comprehend it. I'll be honest with you folks. I try to, but that is as far as I got. I got magnetisms, quantum particles, orientation spinning. That's all I can do for you. And strangely enough, another thing I don't get, and I'm not quite sure how it differs from the quantum spin liquid matter state, which is a phrase of matter that is, one, a mouthful to say, that can be created by connecting and interlacing quantum spins in a magnetic material. Quantum spin liquid, I also know, has a very long range of quantum entanglement and has properties like superconductivity. But maybe the quantum spin Hall state deals with more quote-unquote solids, and the quantum spin liquid matter deals more with quote-unquote liquids. I'll be honest, don't really know. Again, I am a fool with a capital F. And this is probably a dumb question, Nick, but any idea on the difference between quantum spin Hall state or quantum spin liquid matter?
No, I'm just picturing like a top spinning around and then water, like a water flying off a top spinning around. So I don't know what brilliant idea you were hoping for out of me, but you're not going to get it.
It was a shot in the dark. I had nothing to lose. But sticking with shit that I'm too dumb for is another type of matter called strange matter. Yes, it is literally called strange matter. And I think I get it, but then again, I know I'm probably wrong. So strange matter is when quarks, and for those who don't know what quarks are, they're kind of what makes up protons and electrons. They're kind of like if you broke down, you know how everything breaks down? Like you have your glass of water, and inside the water is H2O, and inside the H2O you have oxygen. Inside the oxygen you have, protons, electrons, neutrons. Quarks are if you just broke that down again, pretty much. And when you go back to strange matter is when, and I believe this is hypothetical state of matter. I don't believe we've actually conducted experiments in laboratories yet, so this is all mathematical state matter. But I believe it's when atomic matter is forced all into the nucleus of an atom. Like say your phone, for example, but it's made up solely of quarks. Does that make sense?
Yes, it is. It's condensed. It's like the condensed building blocks.
Yes. So imagine you had the planet Earth and a bunch of satellites around it. Earth will be the protons and neutrons. The satellites will be the electrons. But you kind of squish that all together into the center, into the Earth. But instead of that being protons, neutrons, and electrons, they're quarks. And like I mentioned, quarks are kind of, there's the three types. There's up, down, and strange. Hence the name strange matter. This, again, is kind of when what happens when you force all that into the center. It becomes critically dense. And I have no idea on how much compression it needed, or if it's only be able to do on a electron-based, atom-based, molecule-based. I have no idea the size. I'm very curious about the pressure. I assume it's a super amount. When researching all these states of matter, a lot of them had to do with like black holes, neutron stars, something where it creates an extreme density or pressure. And some of these do exist in the real world, like on Jupiter, for example. These are states of matter that I previously mentioned in earlier in the podcast. It's because it needs that right atmosphere, right density, that right pressure. It needs all these things to come together to form. So, keeping focus and not getting offhand on planets that I want to go to and explore, we're going to stick back to the word super. This time, instead of superfluid, it's supersolid, which is kind of recently discovered. I believe it's been discovered in the last 5 years. Supersolid, at least for me, is a little bit easier to understand. Supersolid is similar to superfluid, like I mentioned earlier, but rather than being a solid like it sounds, it's more of a fluid than solid-like. Superfluid, from my understanding, is just like... Sorry, I mixed that up. Supersolid, from my understanding, is a lot more like superfluid, but instead of the molecules being loose, the molecules are together like a solid. So that liquid inside your coffee that was spinning forever, that was superfluid. With supersolid, it would be, say, like a banana. It's a horrible example, but it's the one that comes out of my head. If you spun a banana, it would spin forever. That's kind of like supersolid is. But it's still like a fluid and still acts like a superfluid, but the atoms are more closer together, more dense, so it's a super solid. It's a bit confusing, but I get why the scientists named it the way they did. Speaking of confusing, hey Nick, you ready to be more confused?
I guess this is the most boring conversation I've ever had with so many times. I've never had this boring a conversation with the word super thrown around so much.
Oh, it's not boring. It's what makes up the universe.
It's not boring, but I've never heard super used in this context. Usually when someone says the word super, it's referring to like a superhero movie. But apparently it's widely used in this field, and I had no idea.
I'm happy you're drinking coffee because I must be luring you to sleep. But maybe I can pep you up. You mentioned superhero. Well, the state of matter might have to deal with superpowers, but there's no super in the name. Nick, let me tell you about the state of matter called time crystals.
I was about... I really thought you were about to say midichlorians.
No, let's be honest, Nick. You're Jar Jar Binks. No, I'm kidding. I take that back. That's mean.
That was uncalled for.
No, but time crystals. It's not some hippie healing crystal method. It's real. Well, it's technically not real because it's still a theory, but I could be wrong on that. I haven't really seen any experimentation done on that. But anyhow, time crystal is a form of crystal structure that is extremely symmetrical but not uniform. So what that means is the physical structure is symmetrical but not in every direction. And it's symmetrical not just in 3D dimension, not just space, but also symmetrical in time. Hence, where the name time crystal comes in. So, this state of matter, rather than, liquid, gas, or solid that occupies 3 dimensions, time crystals occupy 4 dimensions. X, Y, Z, and time. So, hypothetically, with time crystals, you might be able to change and influence time. So, it doesn't have the word super in it, Nick, but it is some superhero kind of stuff.
Yeah, you broke my mind here. So, symmetrical through time. What does that mean? I have no idea.
So, I believe currently there's 18 dimensions in the known universe.
Stands to reason. Continue.
Okay, so I'll explain 4-dimensional space real fast. So, imagine you have a box. It's a see-through box. You got 4 pillars and a bottom. Well, X, Y, and Z is coordinates. So it's, let's say, 5, 10, 20. So it's 5 in, 5 to the right, 10 in, and 20 up. That's a point. Now, say that point is moving up and down, or doing circles, figure eights in the sky. That happens over time. So time, that be that 4th dimension. So now imagine a V. A V is pretty symmetrical. It's not exactly like this for time crystals, but simple. So you have the letter V inside that clear box, and you change the time. So at time 0, you're at your origin, 0, 0 on the grid. And then say you put 10,000 years. It would be symmetrical whether you subtracted 10,000 years or added 10,000 years. That's very simplified and not exactly how it is, but I think that's a very good explanation to get the ball rolling, so to speak.
Gotcha. Makes sense.
Well, speaking of confusing and sticking with the time avenue, It brings us to the Stringnet liquid matter. And yes, that's a real combination of words, ladies and gentlemen. And I don't believe this ties into string theory, which I believe was proven wrong like 3-4 years ago, but I could be easily wrong. Stringnet liquid matter, in simple terms, is matter, but instead of a normal structure, like if you look at a molecule, it's kind of got, squares, rhombus's, hexagons. It's kind of got like a structure in it. You know what I'm talking about, Nick?
I think so.
Okay, when you get like a bunch of atoms together, they kind of make geometric shapes if you look like closely enough.
Yeah.
With Stringnet liquid matter is exactly like normal structure matter, but instead of made of those bonds that form geometric shapes, they're made up of loops. So these so-called loops, being called strings, hence the name Stringnet liquid matter, these Stringnet liquid matter, much more like time crystals, are still hypothetical on how it's supposed to behave, but if you're drawing it, instead of drawing straight lines, you're drawing these curved loops, like deflated balloons almost, to connect things. It's not exactly like this, but I think it's the best way to visually represent it audio-wise. And yeah, I don't get the math of it, to be honest with you. I was looking at some of the equations for it, and I got lost. Like, based on the math, I can understand it's affecting the quantum spin of quantum particle, but how or why, I can't tell you. I'll be honest. When researching this, there are a lot of physics terms and theories that I have never heard of, and I like to stay pretty caught up in the physics world. I like physics quite a bit, but in researching this, I was trying to comprehend it all. And, well, Nick, let's just say I'm very happy I'm drinking right now.
Yep, you and me both.
But, Nick, I want to get your opinion so far of what do you think of all these states of matter?
What do I think in that? Do I think they exist? Do I think, what are they applicable for? I mean, I don't know.
I'll take whatever you give me, baby.
My dumb monkey brain's just making little things in my head. Like for the string one, I just had like a, I don't know, look like a string going back and forth like on a grid through like time. I don't know. I'm working on it.
Okay. At least we're equally confused. But that's it for this episode. If you want to hear more about the strange states of matter that may or may not make up this strange place that we call the universe, well, stay tuned for episode 2 on the states of matter. Thank you all for listening.
Thanks for listening to the Backyard Philosophy Podcast. We rarely finish a podcast without missing a point we wanted to bring up, so let us know what we forgot. And if you have a topic you want us to talk about, let us know at Backyard Philosophy on Instagram and Backyard Philosophy Podcast on Facebook.